Setting up hypothesis tests, Chapter 9. Next couple of weeks we'll be doing a lot of hypothesis testing, so this video will be kind of an introduction to that. Just for purposes of an example, in this video I'm discussing testing hypothesis about a sample proportion, but much of what I say here can be applied to tests about the mean or standard deviation or variance or a correlation coefficient, and a lot of the terminology and theory are similar. So in this example, in section 8.3, based on a sample in which 60 out of 100 patients were cured by a new drug, we concluded with 90% confident that the proportion cured in the long run would be between 0.52 and 0.68. Thus the sample statistic p hat 0.6 tells us with 90% confident that the unknown population parameter p is between 0.52 and 0.68. And this chart here represents the relationship between sample statistics and population parameters. So we're using a sample mean x bar as an estimate for the population mean, represented by the Greek letter mu, lowercase mu. The sample statistic, sample standard deviation s as an estimate for the unknown population standard deviation, sigma. It's the Greek letter lowercase sigma. Population proportion p hat is an estimate for the unknown population proportion p, or in some texts use theta, the Greek letter lowercase theta. The sample proportion r, sample correlation r, is an estimate for the population correlation rho, the Greek letter lowercase rho. So we're using data from the sample to make estimates about the population. To compare a new drug to the 51% cure rate of the old drug, we can set up hypotheses as follows. H naught p equal 0.51, new drug has the same cure rate as the old, versus HA p not equal to 0.51, new drug has a different cure rate than the old drug. So typically the null hypothesis H naught or H0 will have an equal sign in it, so that we have a number to plug into formulas, and typically the alternative hypothesis will have some other symbol in it. The symbols could be a less than symbol, a greater than symbol, or a not equal to symbol. It depends on how the question is worded. Oftentimes, if you're testing a new drug, you would want a greater than symbol here, because you would only be interested in using the new drug if it had a better cure rate than the old drug. So you have to pay attention to how the question is worded. So usually the alternative hypothesis represents what we're trying to prove. So it's it could be less than, greater than, or not equal to symbol. Before testing hypotheses, it's common to establish a desired level of confidence. Usually, oftentimes it's 95%. For this example, we'll use 90%. So 1 minus alpha is 0.9, that's our desired confidence level. Alpha itself, desired significance level, or I like to call it level of doubt. It's represented by the Greek letter alpha. P0, 0.51, that's the proportion we are using for comparison. N equal 100 is the sample size. There are formulas that we'll be using later in Chapter 9, this Chapter 9, to directly test hypotheses. But since we previously computed a confidence interval for this example, we'll use that confidence interval to test the hypotheses. And because P0, which is 0.51, is not between 0.52 and 0.68. We reject H0 with 9% confidence and conclude the cure rate of the new drug is different than the cure rate of the old drug. And just a note, we never accept H0. Either we reject H0 or we don't know. It might be that a larger sample would provide stronger evidence for rejecting H0. So we never accept H0. The following tree shows four possible outcomes for hypothesis testing. Either H0 is true or is not. Either H0 is true or HA is true, and either we don't reject H0 or we reject H0. So there's four possible outcomes here. If the null hypothesis is true and we don't reject H0, that's our confidence level. That's 1 minus alpha. That would be a correct conclusion. If H0 is true and we reject H0, and the chance that can happen would be alpha itself. That's the level of doubt. That's a type 1 error. If HA is true and we don't reject H0, that's a type 2 error. The probability of that happening is the Greek letter beta. Usually beta is not computed because in order to compute beta we would need a specific alternative. So our alternative in this example here was p is not equal to 0.51, but in order to compute beta we'd have to plug in a specific number, maybe for example 0.6 or 0.7 or 0.8 or 0.3 or any number that's different than 0.51, and depending on which number we plugged in, we would get a different number for beta. So beta is not usually computed. Sometimes it's done just so you can plug in different numbers for the parameter under the alternative hypothesis, and just as a what if kind of scenario. What if p was 0.6? What would beta be? What if p was 0.7? What would beta be? So sometimes it's done in that type of context, sort of a what if type of scenario. 1 minus beta would be the power of the test. That's the probability that we reject H0 and if HA is true. So there are two ways that we can reach a correct conclusion, and those probabilities are 1 minus alpha and 1 minus beta. And there's two ways that we can draw an incorrect conclusion. Those probabilities are alpha and beta. The modern researchers often compute a p-value. We didn't do that in this example here, but we use the confidence interval to test the hypotheses. But modern researchers typically compute a p-value, which is the actual probability of a type 1 error, and compare that to alpha. And the p-value, which are desired, so p-value would be our actual level of doubt. We want to compare it to alpha, which is our desired level of doubt. And if the p-value is less than alpha, then we would reject H0. Okay, so that concludes this presentation.